Okay, so the function of U equivalent. So the function of U equivalent, the designer or the researcher can adjust the transient response output. So you can adjust the output either fast, slow, or anything, depends on your design characteristic in U equivalent itself. Okay, so I give you an example. So let's say you have this kind of outputs, three types of output. So you have the output number one, faster. You have the output number two, moderate, and finally the output number three, slowest, the slowest one. So how we want to manage to get this kind of output? So we just adjust or we just tuning at the U equivalent part. Okay, so that's the function of the U equivalent. Okay, and then we go to the second part, the switching function design, SFD. What is the function of the UNT? The function of UNT to make sure the output maintain around the slice phase and achieve the desired condition error equal to 0. So for sure, when we have an output, so we want to make sure our output give an output error equal to 0. So we don't want any error inside our performance. So this is the function of the UNT. So now I can say that the U equivalent used to adjust the transient performance, okay, while the UNT to make sure the error of the output equal to 0. So that's two things. Okay, so this is the USMC structure. So you can see that at the end here, you can find that the error here equal to 0. All right. So this is a U function of UNT. Okay. So firstly, the U equivalent. We go to the part by part lah. So I already tell you or explain to you what is the function or the role of the U equivalent and what is the role of the UNT. Now we go to the U equivalent, how we want to design the equivalent. U equivalent. So let's say U equivalent will force the state move towards to the sliding surface. So this is the sliding surface. Okay. So and then the UNT maintain the state sliding around the sliding surface. Okay. And then this is the hitting sliding surface point. So let's say you have the state trajectory. So this is your output response. Okay, your output response. So now you want to get the 0 error. Firstly, we need to force our output go to the sliding surface. So this is the hitting point. So what is the meaning of this hitting point? So we go to this part. So let's say we have this sliding surface. So let's say if we change the slope of the sliding surface, okay, from here to here, this is the latest sliding surface. So you can see the time travel from the initial condition here become shortest and hitting the sliding surface, and for sure the state trajectories will converge to the origin at this line. Okay, so become fastest. And let's say if we change the slope of the sliding surface to this kind, and then you can see the time travel from the initial condition to the latest sliding surface will become longer. So and then after that it will go to the origin. So you can see that this is how U equivalent can control your transient output performance. Okay, so how we want to adjust the transient output performance? By adjust the sliding surface slope. That's all. So So we go to how we want to design the sliding surface, because we know how we want to manipulate the sliding surface transition response by manipulating the slope. So we need to go to the equation of the U equivalent. Okay, so there are two ways to design the switching surface. The first, we can use SVSS, state variable switching surface, and second part, we can use state error switching surface, SESS. So for sure that ideally, the goal for both approaches are same, to ensure the state or error converge around the sliding surface. So I will show you what is the SVSS, what is the SESS. So this is the equation for the SVSS. Okay, and then after that, next, this is the equation for the SESS. Okay, so you can see that this equation may be quite complicated. Not complicated, I mean, it's quite new for you. But actually, this equation is not new for you. Okay, if you still remember, you learned this equation in your secondary school. Because if we can convert this equation to our familiar equation that we already know, actually SVSS, we can compare these two equations into y equal to mx plus c. Okay, so you can see that the y-axis there, x dot t is y, and e dot t also y. Xt refer to the x-axis, x, and also et refer to the x. And then the slope here for the SVSS is s, and y for the SESS here, I name the slope equal to lambda. And then also c refer to the sliding surface equation. Okay, so how we want to change the slope? We just tuning the s and lambda value only. So this is how we want to make sure the transition response make it slower or faster by change or tuning the s and lambda value. Okay, so why we need to make sure our sliding surface equal to 0? Because you can see the SESS graph here. Our target, we want to make sure the error equal to 0. So by time, you can see that at the end, our state will go to error equal to 0 here. So that's why we need to make sure the sigma, our target, to make sure error equal to the sliding surface equal to 0, because we want to make sure by time the error equal to 0 at the finite value. Okay. According to my research, my PhD research, there are two types, SVSS and SESS. But based on my finding, I can say that SESS perform better or easy to design compared to the SVSS. So let's say if you do some research on the sliding control, so maybe you can go straight forward to the SESS sliding surface design. Okay, why SESS better than SVSS? So the SVSS is easy to design for low order of system only, but complicated for higher order system. However, SESS is less complicated design for both low and higher order of the system. Since my research study is a 6th order of the system, okay, so it means that that's why I choose SESS, because it's easy for me to design my sliding surface. Okay, let's say if I use the SESS, I just need to tune 3 parameters only. If I use SVSS, I need to tune 18 parameters in order to create my sliding surface for my application. All right. So now we go to the second part. We already done for the switching surface. Yep. And now we go to the switching function. Okay. So the switching function, the conventional SMC produce scattering because of the function signal. In the switching function, we can cause wear and tear to, for instance, actuator. However, this function is essential to ensure the state territories move along the sliding surface, and thus chattering elimination techniques are required to solve the drawback. So this is the word. So I will explain to you what is the meaning of this word. So if you still remember during your childhood, you have a pole here, okay, and then you want to adjust the pole upright position, right? So in this case, you need to adjust your hand left and right and so on in order to maintain the pole position at the upright position. So when this is the process we call chattering, okay, chattering here. So for us, when we do it like this for a quite long time, we can get exhausted. So similar to the system, I give example inverted pendulum system. So this is our pendulum. The pendulum must position upright position, and we use let's say the stepper motor, something like that, in order to maintain the position at the upright. So let's say we use the classical or conventional SMC to control the pendulum at the upright position. So it means that the DC motor need to work like this, so it can damage the motor. So in this case, I can say the chattering is the so we need to eliminate the chattering lah, in order to use the SMC to avoid this problem lah. So I can say that the chattering is the main gap in sliding remote control, because many people or many researchers or many students got their PhD, their master degree, their papers and so on because of this, to eliminate the chattering phenomena in the sliding remote control. All right. So now I want to focus on how to eliminate the chattering. What is the existing techniques in order to eliminate the chattering in the sliding remote control? Okay. So you can see that this is the chattering in SMC. This is the look like of the chattering. Because chattering, because the UNT will force the state trajectories because of the signum function to maintain or sliding around the sliding surface. This is the case. Okay. So there are two groups. There are two groups in order to eliminate the chattering. The first group is using the low order sliding remote control, okay, low order, and then the other group by using the higher order sliding remote control, low order and higher order. So there are two groups in order to eliminate the chattering. So inside the low order of sliding remote control, there are many methods and so on, similar to the higher order sliding remote control. There are many methods under the higher order sliding remote control. So firstly, we go to the low order sliding remote control first. Okay. So firstly, we consider the classical. If you want to compare anything, we need to compare to the classical. What is the changes? What is the difference between the modified or the latest elimination technique compared to the classical? So if we go to the classical SMC, you can see that the classical SMC, there are two parts there. If they say K signum sigma T, okay, sigma refer to the sliding surface lah. Okay, so the signum function that cause the chattering. Okay, so in this case, we need to modify the signum function in order to eliminate the chattering. And also in the classical SMC also we have K, chattering amplitude. Okay, let's say this is chattering. We can adjust the chattering amplitude either bigger or smaller, depends on the K, the chattering amplitude. So it means that we also can modify the chattering amplitude in order to eliminate the chattering. So there are two kinds. We can modify in the signal function itself, and also we can modify in the gain or chattering amplitude itself. Okay, there are two. So in this case, I could consider a few examples, or in the literatures, which method modify the signum function and which methods modify the gain. Okay, so we have DBL, decaying boundary layer, and also state dependent boundary layer. So you can see that the signal function now changed to a new signal function. So this is what we call as a boundary layer. So these methods do the modification at the signal function. And then the examples modify the gain here. This is modification at the signal function gain. So RSG relates with state-dependent gains and also linear feedback with switch gain LFSG. Okay, so this is kind of the existing methods. So now you can see that the algorithm is quite straightforward, just about one equation, because this is low order group. So we go to the higher order group. So especially when we go to the higher order, so it means that the algorithm will be more complicated. Okay, so so it's quite complicated lah. So we look at the one example of the higher order SMC. So we have super twisting sliding control as the SMC. So you can see that the equation is quite complicated. Okay, so however, although because of this complicated, so the performance of the higher order SMC is better compared to the low order SMC. So finally, after I do some this research and so on, so I propose a new elimination technique during my study. Okay, so I propose decaying boundary layer and switching function through error feedback. This is my method. So instead of choose one by one, so I focus on the low order element control, and I do the modification at the signal function gain, and also I do the modification at the signal function. So I take those both in order to eliminate the chattering. Okay, so at the end, I found that my proposed method, the new SMC performance are comparable to the higher order SMC. Okay, so this is my method. Okay, so in conclusion, I can say that how we want to design the dynamic control. So this is what I do research. The application is spacecraft, attitude, and orbit. Okay, so I can say that the dynamic control to design it divided into two parts. Firstly, sliding surface design. So for the sliding surface design, in order to design the sliding surface, there are two ways, by using the states and also the states error, SVSS and SESS. As I mentioned earlier, I choose SESS because it's more suitable for my application. And then for the switching surface design, so the problem is chattering gap, but for the researchers in this field, this is not problem, this is advantage. Okay, because we can produce many papers how to solve the chattering because of this thing. So this is a good news for people in this dynamic controller. Okay, and then after that, the solution, there are two kind of solution we can choose among of the others. So we can choose the SMC hybrid with other controllers, and also we do the modification in switching function. So modification in switching function that I explained before. But if we choose the SMC hybrid with other controllers, so example adaptive fuzzy SMC, the problem is we need the computer getting slow, higher computational load, and high power consumption. Okay, so this is, but depends on the application. So let's say if you want to use the adaptive fuzzy SMC and your computer have this kind of capabilities up to the standard, I think you can proceed with the adaptive fuzzy SMC. But in this case, I do the modification in switching function during my PhD study. So there are two types of the boundary, two types of the chattering elimination by using the boundary layer I mentioned earlier, okay, and also adaptive SMC. So, however, there's a problem for the boundary layer and adaptive SMC. The system only robust at this kind of time, and they also have the solution by using the integrated SMC, STSMC, and so on. This kind of the higher order settlement control, and also can use my proposed method in order to solve this kind of problem, robust problem. Okay, so I give you one example lah. This is just a quick thing. How we want to implement the SMC to the system. So I give you SES, attitude control system, for the spacecraft. So this is the kind of your UT available for the spacecraft. We have torque, we have force. So if we convert to the mathematics, it represent the UT. Okay, torque and force represent the UT. So now we want to modify the UT, modify the torque, and modify the force that input to the spacecraft. Okay. So let's say I have the application, spacecraft attitude and orientation model, and I do the modeling and so on by using the Euler equation here, Euler rotation equation here. And then after that, this is the mathematical equation. And the most important part in this mathematical equation is the input here. Okay, because this is rotation, the input is torque. So I need to modify the input. So now there are three kinds of input here: UX1, UX3, and UX5 here. So how I want to implement the sustainable control to this SAOM? So I just replace the UX1 to USMCX1. UX3 now become USMCX3, and UX5 becomes USMCX5. So it means that instead of I have one sliding surface, because there are three inputs for my SAOM model, so I need to have three sliding surface design. So if you still remember that the sliding surface, we have sigma equal to E dot equal to lambda E equal to sigma, something like that. So now I have lambda 1, lambda 2, and lambda 3. So there are three graphs, okay, for the my SMC. So my current works now. So currently I secured, last year, I secured a research grant, FRGS, and the grant, the goal of the research is to analyze the developed algorithm that I proposed in my PhD study from the simulation base, because I just did simulation during my PhD, into the experimental base. So now I want to test, is it working, my method working for the experimental. So this is my target for the FRGS. Okay, and then so because my study I use the spacecraft attitude and orbit model, so it's quite impossible for me. So I replaced the system with a gimbal system. I believe the gimbal system and the SAOM can compare the performance. Okay, so currently I have a student, master student Muhammad Amin. He developed the gimbal system from scratch. So hopefully by next year, we can test my method into the real gimbal system, inshallah. Okay. So the other thing that I also need another student, okay, to do this project for my FRGS. So if we go back here, Euler angle will replace with the quaternions. Quaternion parameter will be considered to design the new switching function. The project is entirely targeted by 2023. So I give you a brief example. What is my another vacancy? So now we can I can say that this is the application. So for my grant, I need to convert this application to a gimbal system. Okay, and then the student need to do the modeling. Instead of using the Euler equation, the student need to use the quaternion, okay, quaternion, in order to develop the mathematical equation. So that's the contribution of the other GRA vacancy lah. All right. So this is my GRA, we can see advertisement. So hopefully anyone would like to share about this. Please do so. Thank you so much. Okay. And then after that, thank you for your attention. That's all for the segment control.